Hello and a very good day to everyone. My name is Brandon Tu Jiang Wei and we are Group 1 from Section 1 Group 1. Today we are presenting our Part B assignment, which is a proposed improvement for plastic bottle filling system using ultrasonic level sensing. So moving on to slide 2, this is our system overview. Our case study focuses on an automated production line controlled by a PLC. The current system operates sequentially. First, a conveyor belt switched by a relay board moves the bottles. At the filling station, a proximity sensor detects the bottle, stopping the conveyor and opening a solenoid valve to dispense the water. Finally, at the capping station, the system uses a pneumatic piston to mount the cap and a DC motor to tighten it up. While the mechanics works well, the control logic has a flaw. And here's where the problem statement kicks in. The critical issue is the timer-based open-loop system. Currently, the valve opens for a fixed time, assuming a constant flow rate. However, physics tells us that flow rate depends on the hydrostatic pressure in the tank, which all of us know that the change of pressure is equals to rho GH. As the tank empties throughout the day, the pressure drops, and then the flow rate decreases. Because the system has no feedback, filling for the same fixed time results in underfilled bottles. To solve this, we need eyes on the process.
Okay, so I'm Chin Hong and I will talk about proposed solution, which is slide 4 and slide 5. So for slide 4, proposed instrumentation. To resolve this inconsistency, we propose implementing a closed-loop feedback system using an industrial ultrasonic level sensor. We classify this device based on two criteria. First, it uses direct sensing, observing the level directly. Second, and most importantly, for beverage, it is a non-contact sensor. It sits above the bottle, ensuring hygiene and preventing cross-contamination. And now we move on to slide 5, working principle. The device works on the time of flight principle. The sensor emits an ultrasonic pulse towards the liquid. This pulse hits the surface and reflects back as an echo. We calculate the distance d using the formula d equals to v times t over 2, where v is the speed of sound. The PLC continuously monitors this distance. As soon as the liquid reaches the set point, the PLC commands the valve to close immediately. This ensures the bottle is full regardless of how slow the water is flowing.
Hi, my name is Muhammad Anihazid bin Muhammad Yusof. So, for this section, I will explain the system schematic and the block diagram of our project. Please refer to first figure in our report. This diagram shows the overall setup of our PLC-based filling and capping system. At the beginning of the conveyor, a proximity sensor is used to detect the presence of a bottle. Once a bottle is detected, the signal is sent to the PLC, which stops the conveyor. Above the bottle, we install an ultrasonic sensor. The sensor is very important because it creates a feedback loop. Instead of filling based on time, the system now fills based on the actual liquid level. When filling starts, the PLC opens the solenoid valve, allowing the liquid to flow into the bottle. The ultrasonic sensor continuously measures the liquid level and sends real-time data back to the PLC. Once the liquid reaches the target height, which set point, the PLC closes the valve automatically. After that, the conveyor restarts and moves the bottle to the capping station, where a pneumatic piston and DC motor perform the capping process. This setup makes the system more accurate, smarter and more reliable compared to a time-based system. Now, moving the other section, which shows the block diagram of our system. This diagram explains the signal flow clearly. First thing first, the detection stage. The proximity sensor detects the bottle and sends a signal to the PLC to start the process. Next, reach the control stage. The PLC acts as the brain of the system. It processes the input and sends commands to the output devices, such as opening the solenoid valve. Then, the feedback stage, which is our new improvement. The ultrasonic sensor continuously measures the liquid level and sends continuous feedback to the PLC. and then the PLC compares the actual level with the target height, which is set point. Finally, the output stage, when the actual level matches the target height, the PLC closes the solenoid valve and restarts the conveyor to move the bottle to the capping station. Overall, this closed-loop system improves accuracy, reduces wastage, and increases automation efficiency. That's all from me. Thank you.
We evaluated this sensor against a traditional mechanical flow switch. The ultrasonic sensor is superwide for 3 reasons. The first one is hygiene. It creates no physical contact with the drink. Second, reliability. It is solid state with no moving parts to jams or wet out. 3. Feasibility. We can change the bottle size instantly by adjusting the set point in the software without moving the halfway. Now, let's move on to our solutions. The ultrasonic sensors offers 4 discrete advantages, which we mentioned just now. The first one is hygiene because it is mounted in the egg grade. It is non-contract. This eliminates the contamination risk common with the mechanical flows. The second one is reliability. It is solid state device with no moving part, meaning it's won't wear out or jams like the mechanical switch. Third, feasibility. The fill levels are digital, so we can switch the bottle size intensely in the software without stopping the line to move the sensor. The last one is the accuracy. The most important, it provides the closed-loop control. It reads the actual level, ensuring the valve only closes when the bottle is truly full, solving the underfilling issues. However, we must manage the 3 specific limitations, which is phone sensitive. The heavier phone can absorb the sound wave, potentially causing a loss of signal. The second one is the obstruction. Condensation or sweat splash on the sensor face can block the sound pulse. The last one is the calibration. Since it relies on the speed of sound, periodic calibration is required to prevent the measurement drift. To mitigate these risks, we propose a simple maintenance strategy. For calibrations, we will perform a non-high test every 3 months to verify accuracy within plus minus 2 millimeters. For maintenance, we require a weekly inspection to clean the sensor face. We will also monitor the echo strength in the PLC to detect weak signals before the line stop. In conclusion, the current time-based system fails because it cannot account for pressure change leading to other underfill bottles. By switching to the ultrasonic closed-loop system, we move from gauging time to measuring level. This guarantees every bottle meets the set point. This, despite minor sensitive to form, the benefit in hygiene accuracy and reduce the waste make this the ideal upgrader for the production line. Thank you, and any question welcome to us.